final person, I will only tell you, look at the acknowledgement and make sure the funding against then he said he has written. I said, fine. Remember, I told you I will not look at it. He submitted. And this paper, he has talked about this nice material, which is actually very nice material. But he's saying too much. He's saying the same material could be used for spectromics. It could be used for electronics. It is also a good photovoltaic material. How can one material do perfect? Not that it can, but it has all those properties. But one of them is more important than the other. Then when you just look at it, you say it will do this and do that, but there's no number, there's no quantitative number. If it is good for photovoltaic, what is their conversion efficiency? If it is good for spectromics, what is their spin polarizability? If it is good for electronics, how? You can't see people prime and have the good of it. Right? Those questions, when you read the report, remember I said, see, I told you, we now killed the other two, killed electronics, we killed photovoltaic, and focused on spectrum. And now did something like testing on the cause of the testing to show how that becomes important information. And send the paper back and all that. So what I'm saying is, paper, not a big paper. Because I will take the one. If you send it to me, I will send it to my students. Because I'm also very but I will also look at it as a progress. Yeah, it's everything. That those are kind of, I'm saying it on the fly, but I was hoping I do all these things and do more today. With Python alone, you can actually put this program and become self-employed. I'm not kidding you. And I will open and show you some of my own profile that I work that is independent of my university. These are conversations with Google, Amazon, Walmart. It's only Python and machine learning. There's also ChatGPT open there. I will show you how we do the exact work that I'm doing that is being used in ChatGPT that you interact with. I've been contributing to ChatGPT for the past 7 years. Like I have the premium version, the one that you pay like $200 a month. That's the one, it really does feel I don't prefer. Right? But what I'm telling you is, with Python and a strong mathematics background, preferably statistics, taking statistics class, R square, RMS, MSc, that is with mean square error, coefficient of correlation, which is R square, standard deviation, variance of estimate. That's actually machine learning. That's machine learning. The other ones are pretty much, common than other ones. If you learn all these things, you create a GitHub profile. Some of us have heard about GitHub. I have my own GitHub page. That's why I put on my code. So create a GitHub page and put what you're doing there. Like when I started machine learning, if you go to my profile, you see a profile, a folder called EDA, Explorational Data Analysis. That is when I started doing my machine. I go to a Kaggle. The Kaggle is a repo where you get high quality data that are open source. I take that Kaggle data, I use it to develop the machine learning algorithm. And when I finish, I do analysis on my own. Based on that data, I will put it there. You put a bunch of things, then I started using it in my research article. So some of all these rules I'm telling you I do, I didn't apply for them. Go and also create a LinkedIn profile. They send me email on LinkedIn and say, hey, we have this problem we are trying to solve. You think you have the right expertise to guide us? Do you have 5 to 6 hours in a week to guide us? I will say yes, I will say no. If I say yes, I could you provide me details of what you like to do? Then they will send details. Right? As Professor said, there was a time I contacted him about one of them. Kind of, my idea then was to enrich students to generate data for me in physics. And I sent it to them. I later got an Indian company. That company made last year $750,000. If you do not know the equivalent of that, it's over $1 billion. That's how much they do. If Zima later brought in one or two students, but then I've already brought in the Indian company. Right? That student, I think, 3 or 4 tasks, because I was paying for each question you sent. I think I was paying another 10,000 or 5,000. So you brought like 5 or 6 questions. It was now when I told you, say, look, I was trying to integrate you guys into it, but maybe I didn't tell you the whole story. This is what I'm looking at. I said, look, I will talk with some about even further. By then I got some Indian university that actually used this. It's not even a company, but we later formed a company. So what I'm saying is, some of all these roles, you do not need to be in the US. You can be anywhere in the world. The only thing you need is a laptop. That's all. That's all you need. That's all you need. Like, for me, Bina is an area I've worked on. Like, the university for me is just because I still want to be in the university. And they are not stressing me. If they are stressing me, I will quit. Do you understand? Why I'm saying this is not to put your mind here, but to tell you that there are possibilities that I will be here. It's just that you do not have the right information and guidance. With the right information and guidance, you can actually stay in this country, have a good career, and do well. Trust me. You can. Because with machine learning is not going away. It has not even gotten to Nigeria. Imagine when it gets to Nigeria, when they will be looking for people that have expertise in that area. Folks like you that took the opportunity that will dive into it. Like when I took 6 months break to do a master's in AI and machine learning. Not with my money, because in the university I didn't want to call it career development money. I took like 5,000 from my career development. I took 6 months to go and do a master because I saw the future. I saw what you can do. With that, I pretty much have a lot of things that comes every now and then. Like Elon Musk has a company they call XAI. I work for that company. I actually took 6 months leave because I have a lot of things I do. XAI. You can work from anywhere. But the problem is the Nigerian university is not there in India. They're not in the US. Because the Indian folks understood in time, they actually have a special program that they just train human resource, that is manpower development, that is channeled to cater for that one. They train to get that job. They train to get that job. You can go to all the CEOs of all the major companies in the world that are doing it in AI are shared by humans. Google, from Google to Yahoo, to Meta, to Oracle, to NVIDIA. They are all Indian, not Indians born in the US. Indians born in India. People. You understand what I'm saying? There's also what we call the COO, Chief Operation Officer. The Chief Operation Officer is like the heart of the company. 95% of the major COOs in the whole world are Indians. You can take your time and just type Google. Think of any big company now. Microsoft. Start from there. or Google that you used to Google. Check it, it's an Indian. And because they already positioned themselves, if you're an Indian man and you are from, are you going to hire a Nigerian or an Indian? So they hire their people to fill in left out. There was a company I worked with one time, they call it VESTA. I was leading their what we call AP testing to mentor this girl. I mentored this girl for like 6 months. The next thing I got was I got signed. Even if you get a chance sometimes to mentor this people, you just mentor them. Once they get to a point where they can fly, and exactly, they tell you, we are doing this and that, and you go back and check. You see, the person that was asking you late night emails, left and right, is the person doing the work we are doing. Because it's his cousin, right? They are not just from India, they are blood related, you know? And this is a story that you get every week. Take your time and look at it. I'm not telling you this to, I don't know how to put it, but I'm telling you this to motivate you that you already have the foundation. I didn't take any other math or physics class beyond the one I took at Bonny State University. No. We have a very strong theoretical background. What we don't have is how to turn into something. How do you turn this? All of us here we solve school equation and derivation. I'm telling you, I teach quantum mechanics 1 and 2 for graduate students. We have never derived that equation. You know what? Derivation is useless. What do I use it for? How do I use it to solve the problem for, say, hydrogen? How do I use this to solve for, say, diatomic system? Nobody has time to derive anything. The student will just get, some of them don't have good math background. In fact, math physics is not compulsory in undergrad for information. So, when you think that, if somebody wants to learn this thing, they learn it and they learn it well. But all those bogus equations, derive, Fermi-Dirac, no. What will you do with the equation? It's already derived. Why do I have to derive it again? Rather, what the type of question you get is actual application of those Bose-Einstein Fermi-Dirac statistics in actual systems. Given a code that would trapped in a potential, describe a scenario or a physical concept or an equation that you can use to describe that system. You see, now the student needs to, that is why we say here we do theory, then we do concept based. Now the student needs to know that you need the Bose-Einstein statistics to describe it. But he doesn't need to know how it is derived. He only needs to know the equation. But the second thing now, you have asked him to think deeply whether it is Fermi-Dirac or not. But now in our own question, the typical question here will sound, derive the Boltzmann statistics equation for hydrogen. You see, it's the same question, but we are tackling to two different. Here you derive a long equation. Here you're asking that person to remember the equation that is used in this scenario and square. See now, these are two different things. So that is a problem we have. We have strong, powerful theoretical background, but the other one is always difficult. And most of our students, if you don't realize this on time, they do struggle. I didn't struggle because, how do I put it? I was around people who told me, who explained to me how the system works. And I had a very good mentor. Besides, was initially from Mali, who explained this, hey, I know you solve this equation, but hey, this, do this and this. So if you don't get this wind on time, you struggle. Because you might think that you stay in a class and the teacher is, you're expecting them to ask if you have experience, no, they just ask crazy question that If you don't know that, true and true, there is no one planet Earth that will answer. Since we don't have direction, I think we just start doing whatever thing that crosses our mind. Until we have a direction and we start doing it. There's a platform I was designing with my sibling before that actually self-teaches you some of this machine learning. But what I hoped is to show practically how we use machine learning in Nigeria. Because the beauty of what you do in machine, remember, some of what is work I tell you, you are not doing material model, it's business. You understand? Some of the things you learn, not some, all the things you learn in machine learning is transferable across the world. Because the concept is the same, the data is different. You understand? When I work with Walmart, I spent 3 months taking a certificate program in marketing and digital marketing. What is ROAS? What is ROAS is return on our ad spend. But the key idea, the key foundational knowledge of how the whole thing works is not something that is with a switch. So learn them as much as you can. And if you know how to program very well in Python, you can even design your own software. You understand? Exactly. You can design your own software. All the software you play with, I design by folks. Right? Like I have an Elastic, which is packed with fast. But I have an SMA2 that you can use with partner. SMA2 calculates strength of material, like the tensile strength, the physical hardness, and all those things. These are Python. It's 100% Python. Right? So there are a bunch of things you can do with and remember, I'm not even good in Python because I'm still learning. That's just the truth. I'm still learning. You can never stop learning how to write code or learning in general, right? There's no matter how you know something, you can never stop reading and trying to learn the next because it's an evolving system. It will leave you, and you have to learn some of them. The core idea will still be there. And remember, learning is not fun. Reading anything is never fun. But the reward will always be there if you know how many years and still be able to do so. So, honestly, I don't know how to proceed. But if you guys let me know, we can do that regardless of whether promises and myself. That is pretty much like, doing stuff on the fly. In an experiment, you have to buy the material, buy chemical and stuff like that. Our own, the only thing we have to worry about is the computational time. That is the HPC. We call it SU time, which most universities we do have a HPC. And if you don't have access to HPC, you can actually write a small proposal and get allocation from the national grid. We do have things like that. That's the type of research we do. Specifically, my group focuses on designing what we call quantum materials, which is leveraging quantum confinement. Quantum confinement is think about a 3D box, right? So if you remove one of the axes, you reduce the hyperspace, that is the dimensionality of that system. If you keep reducing the dimensionality of the system, at the 2D dimension, you run into what we call quantum confinement, which is nothing but how there's no but no chop. Think about when you write your Hamiltonian, H equal to kinetic energy plus potential energy. So So a typical quantum confined system is a scenario whereby the potential energy is far greater than the kinetic energy, right? What that means in actual physical system is that you have electron-electron interaction dominated. In the material modeling world, you now have what we call strongly correlated materials, which theories like density functional theory cannot study because those theories are non-interactive. So those are the type of systems we are generally interested in. A system where strong electron-electron interaction dominates. And when strong electron-electron interaction dominates, new physicist, like he has graduated, is joining Boston College as a postdoc. If you look at it, these are all the whole work he did. You can see this name here, A.C. Luanya. He came to join my group from Twitter. He's also doing very, very well. So these are some of the work that Shehari did. It involved this. This actually got a lot of press. It was published in Science Advance. Think about if you take your periodic table, you go across the periodic table. Elements that are along the same line, you can replace it with the other one. Meaning you can replace sulfur with sodium. S is sodium, S is sulfur, Se is selenium. You can replace selenium with sulfur because they are across the same periodic table. The only difference between them is their atomic radius. But every other meaning the number of electrons available for transport is the same, meaning atom's electron they have is the same, but the radius is different. A scenario like that, we call it isoelectronic group. And here again, couple of 2D structure. These are 2D structure that we studied at high temperature using molecular dynamics. And this right here is actually an experimental verification of this stuff. Meaning after we propose this material computationally, some of our experimental collaborators made the samples and we looked at their major features together. So those are some of them. So as I said, interpolation. Interpolation simply means it's a fancy word for insertion. Meaning, suppose you have two structures stacked vertically. Again, how I wish there is a board and a chalk, but I use my hand. Suppose you have two structures stacked vertically, and there is a space between them. You can throw in molecules or atoms in between that space. Well, for 2D structures, that gap is natural. We call it van der Waal gap. Van der Waal, in the sense, from your van der Waal interaction, it simply means that they are held by weak forces, weak interaction. So because they are held by weak interaction, this layer really don't talk to this layer through any type of chemical process that you can think of. They talk to each other through proximitize effect, meaning through quantum mechanical tonality. That is a typical example of proximitize effect. So that's what we are doing here. So we are using both molecules, atoms, to tune this material. As you can see, this is SMS and this side is GES. So this is sulfur selenide and germanium selenide. These, if you look at your periodic table, these are the group 4 monochalcogen. Mono means it only has one chalcogen. The chalcogen is sulfur selenium telluride, right? So these are monochalcogen. So whatever it is, something like MOS2, those are dichalcogens because it has two chalcogens. So these are group 4 monochalcogens. And these guys are known to be good for, photovoltaic, meaning for solar cell application. But here at the 2D limit, we are interested in, remember I told you, if you go to 2D or 1D, all the theory you know about at the bulk limit becomes irrelevant. You really need to relearn physics because some of the theory we know is no more applicable at reduced dimensionality. So what are they? I already talked about. Think about solar energy, talk about wind, talk about electric cars. Those are areas that some of these technologies are doing. And this is one way. You have a sunlight, you have electricity here, you get some energy. If it overcomes the barrier known as energy barrier, it gets into the landed electrons. If you can do this simple process using sunlight, and it happens many, many times, you're going to generate energy, converting solar energy to electrical energy, which is pretty much what we're using here, right? So that is the same idea. So kind of motivation, but specific for this particular application. Now, this was theorized specifically in 1997 by a bunch of smart folks, where they said, think about what we know from a semiconductor is that you have conduction band, you have valence band. The space between them, which is what I showed you, is known as the energy band gap. Well, in intermediate band systems, the idea is that there is an impurity state lying very low here, closer to the valence state. That you now have what we call two phonon process. So in the case of IV, you do have this type of scenario. These are the intermediate band I'm talking about. It doesn't need to straddle them, meaning it doesn't need to sit central. It can sit closer to the conduction or closer to the valence. If that does happen, it does have this unique feature what we call multi-exciton generation, which is a cascade of exciton. Remember, an exciton is an electron hole pair, meaning an electron and a hole bound together, right? That is an exciton. So when I talk about exciton, imagine a scenario whereby a bound electron is now, think about it as a Cooper pair. But the type of Cooper pair behaves as a boson, while excitons are actually the fermionic equivalent of that because they are both bound states. In terms of Cooper pair, they are boson. These guys are actually fermions. Now, what I've written here is PCE, is power conversion efficiency that I talked about. The theoretical maximum power conversion efficiency we know for a single gap solar cell, example of which is this one, is 32%. Theoretical. Breaking news. Theory is always here. Actual stuff happens here. Meaning if theory gives you 32%, you actually make the sample, you get like 12. God help you get like 18. In fact, the maximum PCE known to date for single gap solar cell is not more than 80%. Right? Well, this guy, because of this combination, because of these two processes that was proposed by Louis and Martin in the late 70s, 1997 to be precise, you can have this MEG, multi-exciton generation, that could actually double this theoretical level. Meaning, if it was 18 before, we might get to 36 in actual material. So that's the type of material we explore. And remember, this right here is theory, meaning pencil and paper work that they have solved Shockley-Paisley equation, or you guys might have had Shockley-Paisley limit in your solid state class. If you are taking any advanced solid state, you might have had Shockley-Paisley. They have solved that equation and gave some numbers early as far back as in the 70s. Now this is the right combination material that have this type of energy gap structured this way. And you might be able to push this limit to go beyond 30%. So putting it this way, there is a limit known as Paisley-Shockley limit that no material could exceed. That is like a threshold that no material, that is material for photovoltaic, cannot exceed that, which is this 32%. So our aim is to break this rule, to come up with an actual material that is not just theory that could break this. So what we did is we took these two group 4 monochalcogenide, two of them, Remember, when you have a layer here and you have a different layer here, what you have is a heterostructure, right? So we took a bi-layer heterostructure to 4 nanometer per layer, and we took copper. If you look at your periodic table, copper is what we refer to as isovalent electron, meaning it gives all electron, it gives out electron. Right? When I mean giving out all its electrons, remember it's only the outermost shell that is available for a chemical reaction. So it gives out the outer electron, meaning in actual sense, if something gives out its electron, it means it overdopes any system that you put it in. Remember, this is not doping. This is the process that this does happen, this interpolation happens, is what we call as electrochemical process. So some call it electrochemical interpolation. It's not a chemical process, meaning it's not an actual chemical reaction because it's being driven by Van der Waals. So we designed this material and we took copper and insert it in between these two Van der Waals. Why? Because a typical Van der Waals gap is of order of 3.5 angstrom. If you put it a little bit, it expands. The copper bond length to salt selenium is about 2%. So it's still a little above the threshold for typical copper bond to form. It does form some bond, or what we call clustering, if you put more copper. I will talk more about it. So what we first did is we put those copper and we did a bunch of calculations. Remember, I told you, when due to quantum confinement, our standard density functional theory becomes ill-defined because it's a non-interactive theory. It cannot capture electron-electron interaction beyond exchange correlation energy, which is very small, only 2%. So we do calculation with our copper. That is what I have. You see this form. Well, when we add that copper, when we interpolate that copper, you start having these isolated bands here. These are what we call impurity bands or defect states. But there's something else. If you just use this functional theory, either local, semi-local, or hybrid. Some of you who might have played with this, we have various so-called Jacob's ladder. You have the local, which are the local density approximation. You have the semi-local, which is the generalized grain approximation. Then you have something like hybrid, like modified Becky-Johnson, or the Kuskera-Skirry-Enzelhoff approach, so-called HSC. Those approaches, when you apply to these guys, including all these hybrids, you get a different geometry. You can see here. This intermediate gap, right, as you can see, what we call onset, meaning it shows that the band is slightly being separated from the conduction band, from the valence band, but it's not full. So we say it shows onset. So we did conclude that these states that are being formed here are driven by many body onset. That is about onset. Onset. Something that is about to start, but hasn't happened. Meaning it's triggering you, but it's not enough to drive it. Does it make sense? We don't do GW that fully accounts for electron-electron interaction. You will never be able to explain the physics. To cut the long story short, when you have an electron hole pair, which is what we call exciton driving any system, you cannot do, I don't know how many, I keep saying it, but I don't know how many of you are solid state condensed matter physics folks. So I try to use, how many of you are condensed matter physics folks? Condensed matter? Condensed matter?
You need to connect further.
Which area are you? Material science. Come on, man. Yeah, condensed matter. Material science is condensed matter, right? Wow. So why I'm asking that is, I'll be using some jargons that are used in material science, but material science, like in transport. Have you heard about Kubo Greenwood? Okay. Have you heard about linear response? Okay. Have you heard about linear response? So what I'm saying is, those type of is the type of optical measurement we have is done by solving what we call the beta circuit equation. It involves heuristic solution of the Dyson's equation, another type of equation that we have solved. I don't know how to explain it. But the way to try to explain it is that you do not have only electron or hole. You have them as a bound state. So Kubo-Greenwood is an ill-defined theory to capture it, because the Kubo-Greenwood only talks about the electron moving here, there becomes a hole. But here they are bound state at the origin. So we solve a particular type of equation as beta circuit equation. How I wish I have both plotted together, the one with linear response and the one with beta circuit. If I plot the one with linear response, you see this structure here, this structure, it will not capture it. It will be flat. In fact, if you capture this structure here, but those are so-called high energy physics. High energy physics, not high energy physics as in terms of high energy physics as the area. It means that it is occurring at high photon energy. If you capture those high photon energy, but those low photon energy, where excitons dominate. Because excitons get destroyed by high energy. Because remember they are bound. If you hit something that is bound, there is possibility that it will break. So you always say, how do you keep excitons bound to room temperature? If you can keep them bound to room temperature, then you're going to create exciton-based devices, which will be a game changer. That has been a challenge. So anyway, that is the type of plot we have. And, as you can see, anybody who remembers very well, who knows the photocatalytic energy of water, what energy in the electron volt do you need to split water into hydrogen and oxygen? 1.23. That's a good number, 1.23. Thank you. So 1.23 is around here. And remember, all these will capture your visible and your IR. This energy here will capture your infrared and your visible. The light and some part of UV, right? The light from sunshine, the one that is useful to human, is the visible, right? Right? The visible is useful. That's the one we use in solar cells. Remember, even though the sun is not shining much, I'm not an expert, but as you know, even though it's not shining much, if you go outside and measure the UV radiation, it is very high. But if you go and look at the energy stored in this solar battery, it's small. But if the sun shines hard, which is the visible one we get, it will charge more. It means that those photovoltaic cells, which is the panel, are designed to operate at that type of energy direction. That's the whole idea. And as simple as it sounds, that is actually how those devices are designed. So what I'm saying here is it captures those images, which is why we now took that material that we created and created a prototype device. This right here is a prototype photovoltaic device that we created on the computer. A transparent electrode is like CD. Cadmium dioxide is a transparent. These are zinc oxide. These are material that allow a lot of energy to pass through. Then we have gold. Anybody who do experiment, the gold electrode you don't joke with it. They should explain better what it is. The gold or silver is always what we use in the electrode instead of orange. Now this is what we call, you can see the zinc oxide window layer. This is what we call the active layer. The active layer is this material that we design. Remember, this is not a lab. This is a prototype that we design on a computer. This calculation is done using another method we call transfer matrix. Anybody have had transfer matrix? Kernel polynomial method. So the transfer matrix method is a numerically exact method that we use to solve any equation, right? So what we did is we take this guy. What do we take? To design this equation, the people are talking about photovoltaic, meaning you need their refractive index, you need their electric function, right? Once I already have these guys, I can get dielectric function. In fact, what the output in this calculation is the dielectric function. But this dielectric function is not just the dielectric function for the exciton. The excitonic dielectric function. Then from there, you can use all these equations that we know and generate your refractive index and the excitation coefficient and other parameters that you need that serve as an input. So for this, we design this device and drive electron, drive current through it, and calculate bunch of quantity. This EQD is equivalent, not one-to-one, is external quantum efficiencies. How good is a device that you can find? Remember, we started this by talking about intermediate band semiconductors. For IB, the value should be greater than 100 because it's a two-phonon process. So we did calculate, and this is the formula to calculate. And I talked about the refractive index from our data survey equation. This guy and a bunch of other parameters. Here we do have a control over how thick this layer can be, and we can play with it. The actual thickness of this layer is about 2 nanometers. That's what we can do it in our calculation, but the one we put in as our input is about 2 nanometers. To cut the long story short, we did show that we can actually design a photovoltaic system with the power external quantum efficiency that is greater than 190. In fact, the EQ is about 190%. And this was published in Science Advance. Anyway, I'm going to skip this. I remember I told you that after we made this material computational, we told our experimental group and they did actually make a sample. And this is the publication that came out of it. Question. When we find the time, tell me stuff. Because I can talk from months tomorrow.
The material you show us, most of them is dropping and single material. So we have most of the time I have a challenge of designing input file, especially for composite. For example, when I have molybdenum sulfide and other metal oxide. So how can I get or generate input file for the calculation?
That's a good question, art, not the science. So making structure is an art, right? I don't know how to answer it because we just learned it. There is no one way of making a structure, right? But some of you use VESTA. Actually, we make most of our structure using VESTA. But we also have written bunch of Python script that does that for us. So, but if you do have a particular one that you're trying to design, if you claim I can ask my student to do for it. But I don't know how to, because it's something you learn. For you to start taking these structures and stacking them together, you need to go back to group theory, right? If you're taking class in group theory, you know the irreducible wage relationship between bunch of materials. How do I rotate a crystal structure to the hexagonal structure, right? Those are things that you learn over time. Secondly, you also need to understand your space group. How many space groups do we have? Do you remember? It's about 230 of them, right? But at least we have 7 basic, right? 7 core and solid. So 7 families, but overall we have 230 various spaces. Those are things you need to spend time reading. It's not taught in any class, but there are resources for that. There's a table called International Table for something crystallography. We have volume 1 to 7. Some of them sell for $8,000. But I do have all the whole courses from the 1 to 4. Those are the books we read. Use it as a reference material. If we really do it at them, so I don't
Try to the particular population.
input file.
Theoretically at 0
Well, for DFT.
Yes,
molecular dynamics. You can incorporate realistic temperature to the simulation by doing molecular dynamics. You do not need, it's not classical and admission molecular dynamics. And then you have, this, you have to do something. You either have to do it, you have to strain it, you have to bunch of infrastructure. I'm going to skip this one. Maybe I look at this one. This has to do with machine learning. Any other question before I skip? That's what this is about. This is also published. It's published in APL machine learning. So this involves, again, these are like dichotomy. The one I think was monocategory. The host to this structure here, the dichotomy, MOS2, HFS2, MOS2, all those ones, right? And involves a bunch of molecules. Here, we are specifically looking at, remember molecules are very large. So we're taking their monomers and isomers, then some chemistry. Meaning we are taking some molecules that do not have many atoms. Why? Because of computational cost. You might not be able to see them. Especially in a high throughput design, meaning you're still getting like 10 to the power, like 1 million structures. You might not be able to finish all of them. So here, as I said, we are taking the MX2, which are the dichotomy, and throwing some organic molecules. Specifically, we focused on planar organic molecules. Those that they are red and flat, so that we'll be able to insert it within the pattern. And that's what we did here. So this is the gap I talked about. This is the one we've already inserted this molecule as an example. And what I'm showing you here is, if we take this MOS2 bilayer, see the gap of MOS2 bilayer. If we throw in a bunch of molecules, you see how we can change the gap to literally anything with that. Right? So that is what I'm trying to say. We use this process as a highly tunable approach to get any type of property that we care about. But how do we do it? Well, I already told we have planar organic model, which is we have a bunch of forces. So we have space of interpolation and MOS. So we have this guy in this basket, this guy in this basket. So what we do is we pick a new micro. We start here. I don't know how to explain this. Not that I don't know how to explain it. It's how to explain it so that it makes sense. Why I'm saying that is there is a machine learning already going on here, but we've not talked about machine learning. Just some time and pay some attention while I try to look through. Now, in a machine learning process, there's what we call training and test. The training is the one where you're doing your simulation. Now, after you finish it on the fly, you test, you get some arrow scale value. This is regression process, for example. You get your arrow scale value here. Suppose you get an arrow scale value of 0.9. You now also do a benchmark on this to see if the accuracy you obtain here matches this. Why do you do that? You do that to avoid what we call overfitting. Usually fits beyond that environment. So if it does give you good value here and not so good value here, that gives you a clue that something has gone. You've done what we call overfitting. Now I've tried, and there are wiggles on it, right? Sometimes the advisor will say, oh, go and interpolate it, or go and do spline. Have you guys heard about spline? Yeah, spline. Cubic spline. There is cubic spline, there are a bunch of other spline. Go and use spline and interpolate it and reduce the noise. And you want the file to pick a particular color. Each time that file picks that particular color, you give that file a gift. That gift is more color. now of a record. And active learning is like that, whereby if the machine learning algorithm gets it, but there's a reward. There's a reward for getting it well. What does that mean? It makes the machine learning to start building and over time keep improving itself. Remember, if you keep trying, this bootstrap ML models is the engine that drives active learning. It means each time that it gets it well, then we give a reward. That reward could be add more data, right? Add more data to build more understanding, complete understanding. As simple as it might look, that is how human brain also learns. That is how human brain also learns every task. Another typical example is a child learning to walk. You put your hand, hey, take it, right? It takes it to give more, right? Before you know it, they start position. Each time the child, or I use foul before, remember, predict EI. EI here is interpolation energy. And interpolation energy is an energy needed to insert this molecule or atom, right? Suppose you have a heterostructure and you insert something. You can calculate the energy cost required to do that. That is what we call interpolation energy. A minus B. That's right. So when you do that, then at some point, which I will show, at some point you can see here, these are your interpolation, these are the errors that are inherent, like kind of your variance in that process. This right here is the actual. Remember, the DFT predicted interpolation energy is the actual, the one you sit down and calculate. The ones inside here are the one from ML prediction, the uncertainty, meaning the difference between the actual and the one that the ML predicted. This is the ML, the one solid line inside here is the ML prediction. As you can see, over time, these are for point of material. It's not that too bad, right? Between the actual DFT calculation. If you're doing this DFT calculation, this machine learning, which is far cheaper, you can now check how much accuracy do I want, or how much accuracy do I lose doing a more complete calculation than just using my ML to predict. You know, for across diverse, this is our top 50. It's not that bad, right? So you can now it gives you an idea of what we call uncertainty quantification. It gives you an idea of how close could you be if you just do the calculation than when you do the prediction using the ML model. As you can see here, for our SCF, because there is an SCF in the active learning, you see the first time, this is the number of, this is the first time is 0 because that's your starting point. You do not have anything to compare with. If you look carefully, at the 5th iteration is able to predict exactly what the 4th iteration predicted, just as the way you do your SCF. I keep pointing at you because it's only that I know that does SCF. So sorry, it's not that, and it's only him that I know and Silver. I don't know most of it, so if I point at him, not that I like you most, but it's folks that I've seen a couple of times. So think about the way you do. Okay, I'll use a different example. All of us have taken math exam. Math, like math 201, whatever. You've done a Newton-Ramsey iterative process. So if you're doing a Newton-Ramsey iterative process, you do this guy, you make a guess, you calculate, right? You make a second guess, you calculate, you compare, right? Now you set your threshold. You said, oh, once the difference between these two calculations are like 10 to the power minus 3, I will stop and take the one before that one as my answer. That's exactly what I'm doing. You say it is compact. Good. That's what we're doing here. We did this 100, we'll stop. We won't take this 5. We'll come back and take the 4th iteration as our combined there. That's exactly what our active learning helps us do. And this is a plot that shows the RMSC, that is the root mean square error. Again, which is what I keep telling you guys, when it comes to machine learning and all this, it's hardcore statistics. Folks who thrive in the area, those who understood their math when they did it, and now learn some Python programming to add it. Every other thing is plug and play. So you can see the RMSC is like 0.6. This straight line, remember, these are bunch of data. This is our top 50. It's not that too nice, but at least, remember, this is just a guide to the eyes, this dashed line. And we can go on and look at some of the energy gap. Again, this is tiny, but it's bolder in the published data. And we look at number of materials, these are a bunch of statistics. Histogram plotting is again done in statistics. Plotting this bar chart is again a statistics process, is not even physics. So we can plot these guys again, these two clusters. These are various molecules, and they are calculated energy gap within our ML. As you can see, this process helps us to minimize false positive. I'll try to explain. In the classification model, it's what we call false positive, true positive, false negative, true negative. Think about you went to a hospital, right? And they ran a test. And the test came that you have malaria. But in actual fact, you have, and they started treating you for malaria. But in actual fact, you have typhoid. What you have in actual statistical model, the way it will be modeled, is that result is false positive. It's misdiagnosis. They show that they have something, but what they are telling you have is not the actual thing that is wrong with you. That is what this thing, false positive, false negative, true negative, is like a plot that tells you what percentage of a data or a stuff that I try to run through it. So this right here is also on, you can download this code on my GitHub and play with it, run with it and see it. There are a bunch of things in it. So we have a pipeline that creates interconnected structure. There are a bunch of other things I don't tell you, like I didn't tell you how we get the molecules. We get the molecules from, there's a repository, those who do biological related stuff or organic chemistry. There is a universal repository known as PubChem. You might have seen PubChem somewhere. PubChem has over billions of molecules. And you can access those molecules by doing a simple API call. API. Meaning writing a small Python script that automatically gets the data that you want from them. Because it's an open source repo. So what it does, instead of downloading all of them, which is billions of gigabytes at a time, we autonomously get the one we want on the fly. But if you don't have internet, you can download it, but if you have internet, that is a smarter way and cheaper way to access it. So that's how we get it. It's a data-driven strategy because the bootstrapping sampling uses what we think about. Let me try this. Think about how you do distribution. You have Gaussian, right? It's a Gaussian distribution. The n tends to 0 and 1. That is 0 mean and whatever, right? Suppose I give you a data and you don't know whether it is Gaussian or proud, meaning beforehand. There's no way you're going to know the type of distribution that it has. So what this active learning, which is what I call bootstrapping, does is that it actually finds it by itself without assuming. That is why it's actually very highly accurate in predicting the actual distribution of the sample without adopting any one of them. So this pipeline helps us to achieve that. So who did this one? This is a manuscript in writing. This is a work by one of my students. He came from Anthony. So again, these are different modulated packaging blah blah for spintronics. Spintronics is, again, before I move on, question. I know I hid a lot of things.
We still have to answer. Doing something.
Yeah, we will try to do it practically. Actually do it how it looks like. But I won't use this one because it might be too complicated for what we want to achieve. What I want to do is keep the one that everybody can follow. Because as I said, we need some level of math. We need some level of programming. We all might not have all of them at the same time. If we pick a sophisticated one that requires something that I don't know, but we look for something in the and use as an example. And as I said, most of all these repositories are open source. You can actually download them. And the rest, when you use pencil and paper to solve for superconductivity, triple state, and stuff like that, we still do those things, but that's the actual fundamental thing. I don't know whether I have it. We specifically write a bunch of Fortran code, breaking news. I mean, yeah, Fortran. We still write codes in Fortran. In fact, all those codes you see are other Fortran or C++. So, it's Fortran. It's 90% Fortran. VESTA is 90% Fortran with C++ and that. So what I'm saying is real physics. These ones are not real physics. Cuts across material science, computer science, industrial system engineering, and soft physics, and math. But hardcore physics are still done with pencil. So again, this again involves the calculation. I think a spontaneous process is a case whereby you do not need external sources to drive the system. Meaning it can occur on its own. Just like if you go to a lab, you can do the experiment with that. However, if it is positive and it's small, it's a signature that you really need either to just hit it or do small things. So that is what I was saying. This cell source, like this guy is negative, this guy is negative. This structure and this structure is generally more stable than this structure because those ones are negative and they will oppose. So this is the size of the Van der Waals gap. Remember I talked about the Van der Waals gap is the gap between these two layers. Meaning, and this is the charge transfer, meaning what is the amount of charge transfer that leaves this molecule to either this layer or this layer. That is what it is. And I'm hoping you will understand what the charge transfer means. The charge transfer, if it is large, it simply means that you have an actual chemical interaction going, meaning it will probably be ionic or covalent bonded. If it is small, that should be Van der Waals. That's what it tries to process. And these are their magnetic structure. Remember, for actual magnetic structure, we have various types of antiferromagnetic compounds. We have the nail, staggered, and striped. I'm not going to go through the details of various antiferromagnetic configurations, but just know we have about 3 or 4 of them. So what do we do here? Because we are trying to get the actual magnetic structure, we are trying to get the easy axis, meaning along which axis do transport move fast. Meaning if you want to make measurement, which axis do you make the measurement? And these are their use of B here is the magnetic moment in ball magnet. So these are telling you which of them are more magnetic, and this is the order. Only 2 of them orders magnetic, the other ones are all under. The cost of this is we tried various places where we get more reaction, more functionalization of the system. You can see here we have G top, S top. A big G top and S top is like functionalizing the 3D structure. We put our dopant there. Here is and try to see what the physics looks like. As you can see, this paper has been published already. This has been published and the second one has been published. You can see this is the clean system, and this is one we have G top. You see this band here, these are impurity states that are occurring. And the secondary impurity states are occurring here for the S top. For the G top, we got what we call a BMS, bipolar magnetic semiconductor. A bipolar magnetic semiconductor, yeah. This is GE top here. This is where you have a BMS. You have a scenario whereby either one of the spin channel does not have what the other spin channel can mirror the other spin channel. As simple as you might know, is something that is sought after in some semiconductor for specific application, like photovoltaic and blah blah. This paper was actually selected as an editor's choice and featured in the book. There are tons of things. I'm just going to stop here. But as you can see, all of them involve 2D structures, functionalization, and the one I think I wanted to get to is this guy. These are so-called topological materials that I told you I would want us to work on. Maybe I play the one. Too much is not good. Just to give you a flavor of the type of work we do in general. And when we compare, we try to do the actual machine learning. I'll try to get one, and I'll show you where I downloaded it from. And we set up our Google Colab, and we'll do it together. Is that okay? Question.
About the DMS. What's the difference between the DMS and the DMS?
DMS. What is DMS? Dilute magnetic. Dilute magnetic semiconductor is simply a scenario whereby a classical semiconductor upon doping becomes magnetic. For example, gallium arsenide. If you take a gallium arsenide and dope it with the optimal value is 4 to 5% manganese, it becomes a DMS, it becomes dilute magnetic semiconductor. In case of dilute magnetic semiconductor, it will look like this. It will just look like a polarized system. But BMS, we have this scenario whereby the other one nothing is there. It's pretty much flat, as you can see. And you have this guy emerging on the other side. So I would say that a BMS is a subset of a DMS, but not vice versa. Because when we say dilute, it simply means that a small percentage of a magnetic atom turns it to become magnetic. You understand? That's why it's actually called that. Dilute is not driven by the high constitution of the magnetic atom. It's driven by a very tiny percentage of the magnetic atom in the system. We'll go and grab something and eat. Let's maybe reconvene one, that do something to the 4. Looks for it. Right? So let's reconvene at 1. Map the concept linearly of the topic, highlight contradictions, and these are some of the tricks you can use. There's semantic scholar, there's site.ai, connect, then deliverable crystal synthesis, not a summary that justify your questions originally. So why this is critical is you cannot answer these questions if you don't know what your result is. Meaning you literally have to have completely finished writing your result and discussion session before you try to do literature. You need to be careful with that. You need to define your core claim. What is it that you just found, or what is the main hypothesis that you want to build around? That should, get re-emphasized almost every 2 paragraphs. So think about referees. You do not expect referees to sit down and read your whole paper back to back, right? Nobody does that, including myself. I look at the abstract and see, has this been done? Yes, it has been done. Or I'll look at the journal. This is PR. PR means novelty and usefulness. If this has been done and you're not adding anything new, it's reject. Not even a major revision. because it's not driving any new thing. There's nothing that is adding. We call it incremental addition. It's not adding anything new. So those type of paper does not belong to peer, right? So the calculation that nobody can reproduce. Science is reproducible. If you do a calculation here, someone in Japan should be able to reproduce your data within the same numerical uncertainty under the same condition you've done your calculation. That is what reproducibility is. So this must be transparent, generalizable, and statistically sound. This fair principle, do you guys know findable? Five means findable, accessible, interpretable, reusable. It's a concept that is being championed by all the rule funding agencies, whereby they encourage everybody to make their actual data they use in producing their plots accessible for others to reuse. Why that is important in the era of machine learning, I do not need to have to extract data from your paper and just from any repo where you keep it and add it as part of my machine learning pipeline. So it's been encouraged. Whenever you hear fair principle, it means your data is findable, the data is accessible, the data is reproducible. The best practice means if I'm writing a paper, if you look at some of the papers, most of the papers we've written, if you look at the tick, I'll tell you why most papers get rejected easily. Not because of the science too. If I look at that paper, I'll look at the figures you have, and you have tick marks. In your figure 1, you have tick marks. In figure 2, no tick marks. In figure 3, no tick marks. I'm going to reject it. It shows you don't pay attention to detail. That's just the truth. As simple as that can sound, if you take any paper in physical review, DL or something, and look at all the whole plots, the size is identical. None of them is bigger than the other one, unless if you have a panel of figures. If you're using a tick mark, make sure you use tick mark throughout your whole figures. If you use bold to bold the legends, bold all of it. If you bold here, you don't bold there. It's in shifting stuff. Those things they pay attention to. That's what I mean by structure figures and tables before writing results. That's what I was saying. And those tables must, if you just single tables and single figures, they must be same size throughout. All. So pay attention to that. You see what I just said? The use of Python is one tool, the new plot to plot production data. I do this because you cannot automate it. And also the resolution, the standard resolution of figures is 30 dpi, 300 dpi. Go for 450, 600 should you lose some quality of your figure when you're transferring to other environments. Those are also important. So compare against at least 2 state of the art baseline. Those baselines are journal specification. There are other secondary journal specifications like the must pay attention. Every result should serve as a piece of evidence for or against your hypothesis. Meaning, that is why another rule. You know when you see a figure, say figure 1, plot of you see PDF, you just the DFT result for CUCO, something like that. You know, the rule for most journals is that every figure must tell a story. Meaning, I should look at a figure, including the caption, and I do not have to read it anywhere in the manuscript to be able to understand that figure. Meaning, both acronyms and everything must be fully defined in your caption for every figure. I'm not making sense. Don't use abbreviation in your figure, even though you define the abbreviation sound. Anybody looking at your figure should not have to go inside the manuscript to get which acronym you define as a caption in your figure. Here are your table as well. It must be what self-explanatory on its own, without having to depend on any other. Including the caption. That's what I mean. The caption must contain every information that the page is. No, because they're independent. What if I'm looking at the figure every figure, every table must be self-explanatory, independent of each other. Meaning, if you use, I just give an example. You can't come to this figure and say the PB DFT data for blah blah. Even though you've defined PDF DFT somewhere in your main manuscript, that figure is a piece of art, is evidence against for. That is for against the hypothesis you are driving. You must be able to tell the conclusion independent of the actual textual data. Does it make sense?
Yes, at the end of the day, we still have some of them that do explain within the text.
That's what I just said.
Some journals, they have the figure well explained, the details in which some too, they just caption it and they explain.
It's not journals, it's individuals. And it gets passed for depending on who reviewed it. But if you're trying to publish the physical review, any of them, PRL, PRB, PRA, PRX, any of them. If you're trying to publish in Applied Physics letter, Journal of Applied Physics, if you're trying to publish in any of the Material Today journal, simply put, if you're trying to publish in any R1 journal and you do not follow these rules, if you submit this paper now, you get a response tomorrow morning. And that response will be rejected.
Because there's a figure where possibly that is naming your figure with maybe an alphabet or something like that. Maybe just figure A or something like that.
Yeah, figure A has nothing. I don't know what figure A is. That's what I'm trying to explain. It should be self-explanatory. I'll try to show an example in my own actual data. Then it's right. There's a data, so this first guy here, this is an undergraduate. The first author that I just highlighted, is an undergraduate student. That undergraduate student is being mentored by this guy and this guy, Anthony. Okay, now I'm doing bunch of. Okay. Yeah, it's like that. Overlay is this is the premium version, but you can use overlay, and that's what we're going to use in writing our paper. We do not. I personally don't use Word to write. And as you can see, it gets organized nicely. So what I'm trying to explain, you asked that question. What I'm trying to explain is, if you read this caption here, you don't have to read anywhere in the manuscript to understand what all this table is. I could have said the periodic table for XYZ blah blah, full stop. But this table with the name and everything is self-explanatory. So you go to another one. Remember this here, and we must define it completely.
In the table.
And that's exactly stability classification of this based on energetic amount. Remember, I've defined some of all this as acronym in the main manuscript. But I'm defining this PB plus SOC. Did you see? This PB plus SOC have been defined in the main manuscript. I could have just said PB plus SOC, but it's not. That's not the way you write caption. Density-based cluster variance. And if I find it here now, let me see. Did you see? You see, I used it here. What I'm simply saying is, it's not enough to just throw acronym in the caption. You must completely define it here in the caption. We can go on and on. See, this is a long term. You see? You see work function. Remember, I've defined fact, even where I calculated the work function in the main manuscript. But in this table, as a rule, you must completely define it. You're fine if you're pursuing Q2.
Actually, the standard.
There's no standard. There's no standard known. Standard known, remember, if you look at the figure,
Like, so I know about hydrogen now. Instead of mentioning hydrogen, you use H.
It's not an acronym. That's the name. H is the name. You can use H or hydrogen. Remember, if you look at some of 2D has been adopted as no more an acronym, but actually a name. Do you understand what I'm saying? Hydrogen, H and full hydrogen are both names. It's not an acronym. You understand what I'm saying? That's the name. It's not an acronym. Anyway you use an acronym, you must fully define as a rule. Am I making sense? So you can go on, and you see how we've met. But remember, we started working on this paper like 4 or 5 months ago. If you see there are still red, those are places they have put red and asking me questions to take a look at. They don't understand. You understand? So that's the way we write. When I was coming in, I personally have spent a combined, because I gauged my hours, a combined 42 hours working on this paper. On my own part alone. When we were coming, my flight was 11 hours. I spent 9 hours of that looking at this paper, writing. So writing the paper is not you copy here, you paste here, you get here, you put here. You need to sit down and ask yourself questions. Try to answer it. Once you are able to answer your own question, then you know you're making progress. So I can go on and on. That's how we structure, we try to write all this thing. And that's it. We use latex. I'm telling you, it's not that hard to use latex. Why this is more useful is you can actually pick, there's no internet, I think we lost it. Okay, for that. You can actually pick the journal template that you want to use. And overlay has been nice because this right here is synchronous, meaning two people can work on it at the same time and you know exactly what that person is doing. So it helps for collaborating better. Question so that we can switch here.
So you make mention of writing. When you are writing, you don't actually write something that has been published before.
No, I didn't say something. What I said is you need to look at what has been published and design what is the question unsolved problem in that thing that has been published that you are trying to address.
Because my question is, possibly, let's assume you repeated the work but get a different answer. Is it not acceptable?
It's acceptable, but the different answer must be justified for or against. So which is your hypothesis? The hypothesis is I now did this calculation and I have a different answer. The question now is the guy who did it before, what did he do wrong that you must be aware of? That's what you need to say in your own paper. That I did it and it's a different result and this is my data is not enough. Right? You need to show why that one was wrong and yours is correct and where should you go from here. That's the whole idea. Am I making sense?
You're saying that you work on the day result before literature review. It's not going to make you go back to adjusting some of the results.
No, literature review does not make you adjust something in your result. How?
I thought in literature review we also see more specifically the result before according the close result according to what you actually working on.
Okay, let me put it this way. That I said you do bottom up does not mean you don't read literature before you write those results. It just means you don't start writing. Do you understand? You can't, when you're writing your results and discussion, you're looking at literature and seeing what people are doing. But you shouldn't start writing your literature review as part of your manuscript when you don't have the result, because it's your result that will guide how you frame the argument. Just like what you said. If we go to our own literature review, because we are pretty close, which is why we added literature review, and abstract is the last one. Title is the last one after. So if you look at here, you will see how we try to frame it. Again, I'm using a working document. I will try to find something. The keyword I want to find is why. It remains central to spectrum. The two-dimensional analog referred to as fusion layers are increasingly being explored for quantum technology that benefits from reduced dimensionality. These mono or few layer disguise structures preserve magnetic tunability of their bulk parts while gaining new advantage from 3D confinement, such as this, right? Such properties make fish bearing highly attractive. Given the vast chemical and this is systematic, you see, here we are showing why we are doing this. You said, given the vast, you said a systematic high throughput is essential to efficiently identify viable candidates and avoid the limitations of Edisonian computational synthesis. Edisonian computational synthesis is a trial and error method. Do you understand? So you see, this is why we are telling them why we are actually doing this. That should come almost the last paragraph in the literature. And that's why it said, you continue. While it might not now, after that, you now put some results of what you found. You said, after you see that, you see what will follow. To this end, we present a comprehensive high throughput investigation of the structural, magnetic, electronic, and topological properties of this gas. Our objective is to uncover underlying design principles and identify viable candidates for experimental realization across a broad chemical space. To achieve this, we employ a high throughput first principle screening framework to computationally synthesize and characterize 839 candidate discards. Each structure is systematically evaluated for their thermodynamic, mechanical, blah, blah, blah. And the screening result is curated set of blah, blah, blah. Yeah. So now we started with 800 and something. We ended up with 605 has been mechanically and thermodynamically stable. We say among these 605 stable which we are in, our analysis revealed a diverse spectrum of quantum functionalities. Specifically, 46 compounds exhibit half metallicity, characterized by complete spin polarization on the Fermi level, making them suitable for spin field. Additionally, 15 structures display ultra-low work functions, positioning them as candidates for electron emission and field-assisted transport. Over 100 monolayer exhibit structural substantial magnetic moment greater than 1 bar magnet, indicating this. While a minority of the system retains semiconductors, the majority displays semi-metallic character with pronounced spin symmetry. Notably, our topological band analysis, you now have to present the result that you have as part of this process. That will close the last paragraph, as you can see. Then you go to the method and explain how you do it. But all this should not come when you haven't really analyzed your data. Not that people don't do it the other way, but I think it's a bad way of writing a paper. Because after you have the data, the literature review you have must support the actual result you have. That's why I said that. Any other question?
Thank you. Still, this functional study is doing like long hour study, discovered for long hour. But is there any possible way to control the experimental parameters? Especially, for example, let me explain something about molecular sulfide. When we run it in computational, like it's possible to get the exact sulfide of that molecule. But when we come to lab, getting molybdenum sulfide is not easy because of those different parameters. Environmental parameters.
You mean in actual lab?
Yeah, in actual lab. So, like, after running this calculation, the outcome of the result from this competition, is there any way we can integrate it with lab?
Yes,
experimental.
I talked about we did the simulation and the fabricated. Now, what you're trying to explain, and you're saying, well, if I go to the lab and try to make MOS2, there might be some, unintentional defect or something that could find this out, right?
Yeah, this calculation, will you consider those factors?
So, you can, but it's not our problem. I will explain why I said it. If you go to lab to make any sample, your STM and other fancy stuff that you guys use will tell us the purity of the sample, right? If you say this sample contains this specific and that, so when you get your sample, if you tell us how pure it is, then we can design our simulation to benchmark that. Do you understand what I'm saying?
Yes. My own is not
So
only
you need a
unintentional impurities. I'm not talking about unintentional impurities. Like to set to optimize the parameter, for example,
Which parameter?
temperature.
In the lab, for those ones are easy. You can put the cryogenic temperature, silver and the rest are doing. You know the temperature you're doing the experiment, right? You have total control over temperature. Your glove box, you know the pressure, it is 10 to the power minus 15 or so, whatever. So the experiment is if it's not controlled, then it is not reproducible. So that is what every calculation also has its own.
We need to do experiment again and again to control those
But
parameters.
that's you guys' problem. It's not my problem. Right? If you take any equipment, if you tell it the operational temperature, you can set it based on that. And every material has its own, depending on how you're doing, are you doing a kneading or whatever. They have all those fancy numbers that you guys punch, right? But I don't know how you guys do, but if you can't get it right, I don't care. So mine is just a good calculation. And if you tell me number, because when the experimentalists finish their work, they will say, we grow this sample at so temperature. And we did this and we did that. We carried the RC analysis and we saw it has so percentage pure. It contains this, it contains that, it contains that. That must be provided too in experiment, right? But for us, if we saw MOS2, this MO is pristine MOS2, nothing else.
So what this study will help me? I'm an experimentalist. What am I getting from this experiment?
Whatever you tell me to simulate is what I will simulate.
When you are done with the lab, I think
You tell me
work with
exactly.
the lab, they give
finish
many
with your lab,
parameters and the
you
result.
provide me your.
If I finish the synthesis, I have the material already. If I finish the synthesis, I can go and check the purity of the material.
Yeah,
If it is pure,
that's what
if it
you
is
do.
pure, no need of coming to competition.
No. No, you cannot. There are many experimental data that are still not even explained yet, both from experiment and theory. One, SRUOT. There's what we call Van Hook singularity that occurs around the field. They don't know where it is coming from. And another example. You've heard about high TC footprint. Do you think high TC footprint was explained by experiment? No, it was explained by simple calculation using Hubbard model. It doesn't work like that. There are 1,001 data you have to explain. Only theory can do that.
So just to understand the result.
Yeah, but that's, if you don't understand the result, it's just an art. It's not right. It's not just.
Yeah,
it is
the
key.
I was thinking a predictive aspect, like instead of wasting my chemical, my time.
That's the whole idea.
If this study can give me the exact parameter, I will get.
We can give you exact parameter that you measure. Remember here we talked about 605 stable structures. Throughout his career experimentally, you'll be able to grow 605 samples. Exactly. But that's what an REU student and two student did in less than a year. Do you understand? That is how we say to avoid a Wilsonian calculation is a trial and error process, whereby you check, you do it, and you check. You can do that computationally over and over, but experimentally, you need the backing of the federal government to survive that because you need to buy a lot of chemicals. So what we try to help solve is to stop trial and error, to reduce costs and accelerate discovery. That's what computation does.
So, Professor, we use this computational to ascertain what we actually want to do.
Yes.
Before we now get to the lab.
Yes. We try to narrow the number.
Because I remember, like in some electronics, there are some softwares that you can use to design a circuit. Actually know what you have to do within the circuit.
You can't even go to the lab bench to do it without doing what you just explained. Yeah. It's the same idea.
So I'm looking at it that we can probably say from the further suggestion studies on the work. For example, this one, there are some recommendations that you have down there for further studies.
So you want me to go back there?
No, I'm just stating that from that further recommendation studies on those on that one, somebody can be able to trace, get literature review from this your work or any other relative work to this particular topic of yours in the process of gathering this literature review.
Remember, when I mean finish discussing, there's nothing like finish discussing the result of you submit your paper. Meaning it is always an ongoing process. What I mean by that, you should get a complete understanding of your hypothesis, the problem you're trying to solve, and write it down to a point whereby you should be able to relate it to existing literature and argue against and for what is already known. That's what I mean. An actual overriding of the paper, once you fill in all those that you still have to go back again. You have in my place for my case. You have processes. After you read it on the screen, you must, when I mean you must print it, hard copy, single-sided, so that you'll be able to read line by line. You now read line by line and correct syntax. There's what we call floating argument. You might have shuffling, you have some incoherent or incomplete discussion. You need to now clean all those things one by one. Use red mark and mark all of them. The writing of the paper is the whole process. It's not something you just go to that. So again, that's the way personally for me, and having seen what others do, having reviewed tons of paper, having been an editor for many journals, that is what we look for. So what I'm telling you is based on my own experience and having interacted with others, the way I think is the best practice. Remember, there's no one way of doing anything, but there's always best practice that everybody should aim to achieve. It might be difficult, but trust me, when you finish the third iteration of your paper, you need third, fourth, fifth iteration of your paper before it becomes ready for submission. When you get to the third iteration, you start feeling some closure that this paper is not making sense, right? At the beginning, it might not make sense. You started writing a paper that my student just came and said, I can't just wrap my mind around what I want to talk about. I think this is true. I said, okay, what does your result look like? He said, I got this, I got that. I said, why not focus on this? Right? There are almost always, has always been the case. I'm not saying it is easy, but over time, as you keep practicing, it becomes part and parcel of you that you actually do this as part of your everyday life.
So my question is, for someone that went through the, let me call it the wrong route of writing a paper, maybe starting with literature review first, instead of carrying out experiments to get the required data. And then at the end of the day, what the person reviewed turned out not to be feasible in the result. But is it acceptable for that person to actually remove some of
It's not acceptable, that's the only choice, unless if you don't want to publish the paper. Once you do it and you see that the literature review you already did does not flow with, you literally have to yank it off and start writing another one. That's the whole idea. You don't want to waste time on things that could have actually been done more efficiently. So that's the whole idea. You don't want to waste your time. You need to yank it off and write it. And we've done, if you go back to the actual, you just have deleted all of them. I will show you something. Let me go back to editor and people. I've removed most of the. Let me go to history so that the network has gone. You might need to come and put that your PIN or password. What I'm trying to show you is that it's okay to yank off some facts. In fact, some discussion. When you start discussing, you see that it is becoming too convoluted.
yes.
And everybody who has Gmail has Google Color. So is my drive. And this is my, I have two here because I renamed my own collab. So that I'll be able to control. Everything that I do, I kind of incorporate it from. So I'm going to take this 2D material. I will show you where it is in the link. This is my repo, my GitHub. If I take, let me take this one. So if you go to any repo, it will tell you the data set, right? And this was like 4 days ago. So this is the data set. There's just a lot of it. But there's a smarter way to get this. The smarter way to get this is to go back. If you want to get this repo, you just come here. You can download it as a zip file, or you can use Git-clone. I copied it now. Since I have a terminal, I can go to my terminal. Let me go to download. I don't think I have it either. I don't have it. I don't have it. So I don't have Git-clone here. This is a new laptop. So I wanted to use the command line to do it. I can install it and use Git-clone, but all I just have to do is to hit download. Then if you download all the full file, everything at the same time. I can start from already prepared one, but I want us to start it from scratch so that you see how I get data from any repository. You see, I went here and get the code. Wait, it's downloading now. It has finished downloading. So I go back here. You see, this is it right here. Right? That's it there. I have to unzip it. Unzip is unzip. So I do 2D. It has unzipped all of it. So it unzipped it to this part. I will see it with that. So this, you can see it now. If I do PD doc, you can see it. I'm now inside that directory. I can see. Again, the problem now is I'm not using Linux command. Or 100% of here are actually using Windows. Yes. So that is the problem. So that is the problem. But let me do it in Windows. I won't use this one. Let me try to do Windows. But do you understand up to the point where we downloaded it? How I wish we still have this WhatsApp group. I could share the link. You see this picture? Just it's still there. Yes. And I will come out this Google provide. We are trying to get to where we can do machine learning. We've already downloaded the data somewhere, but now we need to do it. Can you look here? Web browser has no memory where you are, right? If I log into Collab now, because the email is already, my Gmail is already signed in into process. So it will probably hook me up to the collab environment.
I'm looking at different background.
What do you mean by different background? Already, like I said, I'm already logged into collab. I mean, into G. That is why it's kind of intertwined. I can pull the data from my drive autonomously within the Google Collab account. Again, you must sign in to be able to retain whatever thing you're doing. All of you have Gmail accounts. Even I have a subscription for the premium version, but the free version will do what we want to do just fine. The premium version gives you a GPU environment that you can actually start running and close your laptop and run. There are many ways we can start now. Remember, we've already downloaded a file. Okay, let's now book and drive. Meaning your own Google Drive. You can just upload notebook. You can save a copy in Drive. Whenever you save it in a Drive, it will appear in your Drive. You can also save a copy as a GitHub list. Meaning, if you connected your GitHub, if you save anything here, it will appear in the GitHub. But let's not get to that one. That one is a little more.
I wonder how you move from this.
Right? Finish. Now you can unzip it. Did I lose anybody?
Yes.
Good. So go to code.
Okay.
Can you just look up? If you look up, you'll be able to see.
Click code first.
Okay, look, watch me. This is code. Right? If I click on that code, I get this. So then I might be able to help. Don't worry, we'll find it until you get something. Now click on code. Then download zip. Can't you see download zip as the last one? Do something. I've already unzipped, right? We now need to bring the files to within the collab environment. Right? There are many ways you can do that. But let's take the easy one. The easy one is manual level. Which is you upload everything manually. The more efficient one is to use still within your Google Drive, Google Connect, and autonomously do, but that one involves code. Let's leave that one for now. Let's do the simple one first. Since I already downloaded the file, all I can do is I come to a file, say open notebook, right? Or then there's also upload notebook. So we're going to do upload notebook. I think you're recording it, right?
Yes.
Okay, this is good. So let's use upload notebook. Why? Because we already have a notebook that came as part of the file we downloaded. Are you guys there? So if I click upload down, then it's going to ask it. So let's do this. Yeah, you see what I just said? Click file and then upload notebook. That right? But if you just look at it, you see what I'm doing. There are many. So how do you upload a file? Now you can drag and drop, or you click and upload it, right? This is a file I want to drop. This is it here. So the one, this is an interactive Python notebook. IPYLB is a Python file, but in notebook extension. So if I just do this now, if I drag this guy, this is what I did, and drop it here. I'm opening it. It does have it. It's not rocket science, right? So you did download that to this stage. If you download it and unzip it, it does have it.
Okay. When we download it,
Person who is on the same page.
Huh?
Which one? Which
No,
one?
one is not
When
a
what you can look at two back, whatever, what we did in this notebook. This is an actual, this is a part of a published paper. This right here. I'm going to close this part so that we have more space. The first thing you normally do, because it's a published paper, we've added some sessions to guide them. Meaning, if you click in the way we've done it, if you click in any of this, it will take you to where that part is. It should respond, but the internet is slow. Once you click on it, it is rolled to the one that has got blah blah blah. This was it. You have SQL, you have NumPy, Matplotlib, and NumPy.
Apart from intellectual expertise, I'm told that you also came along with the system for us to use, and that's what we are doing here. And we appreciate all the sacrifices. Coming to Nsukka, for anybody who is not in Nigeria, it's news. It's even the biggest of sacrifices you can make. So we appreciate that. It's just a token. And wherever you keep it, you may not be able to carry it. You know, appreciate. In Igbo parlance, they say, no way back, I will mind. You don't have to ask me. Accept us for what we are. The deep in our hearts, we appreciate what we are doing. Thank you very much. Having misses and progress. Thank you very
What's inside it? Seaborn is a plotting tool, like similar to Matplotlib. Seaborn has more superior color distribution that you can use to produce more high quality work. And a bunch of others. I will try to explain those ones. Those are specialized type of libraries. So if you look at from SK-led model select, we're importing cross-validation, cross-val predict, k-fold, repeated k-fold, bunch of things. How do I explain all these things and make it make sense? Okay, I'll try. Think about when you take a sample, right? And you do measurement. So measurement that you did is you want to get an average. If the sample you keep to getting the average is done random. Now, if you do that one time, statistics tells us that your error, your uncertainty will be large because you don't have any way of, you don't have any distribution that you average over to reduce the noise, potential noise. Now, these guys that we have here, machine learning tools that have been designed to help us make measurements 10, 20, depending on how you do it. Could you do 10 or 20? It always be reflective of how large your sample statistic, that your sample data is. Meaning if you have 100 data points, you shouldn't do k-fold or repeated k-fold of 20, because that would be 100 divided by 20. 100 divided by 20 is what? 5. It simply means that each chunk is only 5 data points, which is too small. So 10 will not be a good number. If you have a small data set, you use a smaller k-fold number of 5. Or 5 is a good number there, so that you have enough thing to average over a number of times. The k-fold and repeated k-fold are various versions of the same process. Think about the way we talked about PD, LD, those are like various versions of improvement over the other one. There are other ones. There are other types of K4 that are out there. This is just two. And there are other versions that are not K4 that are other types of implementation. So what?
The sampling process, we don't hear this random.
Sampling process. Yes, machine learning is a random process. You will see somewhere I might have already defined a random seed. Let me see if I define a random seed. Random is a stochastical sampling process, which is random, meaning if you run it and I run it, we are not supposed to get exactly the same number. But let's say if we've done that process using the same random seed. I don't think I have a random seed. Cross validation simply means you are trying to benchmark how accurate this K-fold, each of these, if you divide by 5, each of these guys is going to produce an arrow square value if we're doing a regression, right? The K-fold will automatically get how accurate each of these are with respect to the test sample on the front. Remember, each of these is shared here are what we call the training set. While the other one that you keep aside, we talked about it earlier on, the one you keep aside, like 20-30% of your whole data set that you use to validate your result, is a test set. Those test sets, as you're doing your machine learning training, you can use it within the same pipeline when you're still training to check how accurate it is doing for each of these K4. That process gives is what cross-val score and cross-val predict. The cross-val predict will do the actual fitting, the machine learning, for the test data. Then the cross-val score will give you the actual arrow square value if you're doing regression. If you're doing a clustering, it will give you your F1 score or record of precision. Again, these are all statistical terms. It's not even a machine learning term, which is why I was emphasizing before. It's important we look at what we did in our statistics and add more to them because it's a term that will be a recurring decimal. We start doing this. You have a data set, as you see shortly, that is not numeric. Python does not understand number force. Level encoder will change it to 0 and 1 so that Python will understand. Am I making sense? But not Python, so that generic machine learning will understand it because deep learning does not care. Deep learning takes in everything it throws into it. But we're not going to do that. I'm going to skip some of all the ones. This is the linear model. This is the classical linear C that we do in math class. This linear model is now XBoost and LightGBM are type of learning. Let me see what then I try to explain. Boost and GBM means. I will use English language somehow on my first explain. Maybe somebody will give me a flavor of what it means. There's this saying in Igbo, collection of people that once they come together, they become stronger. That is what these two type of machine learning models. Each of them are weak, but if they come collectively, they become strong. Means this guy might be doing a prediction, he's getting gives you something more statistically accurate because it has this kind of variance and statistical. So those are we call them boosting and bagging models. All this one that you see, again, these are mean square error and plotted mean absolute error. Right? So these one are just matplotlib. So I can remove that one. It's just you want to put that to enable matplotlib when your plotting is displayed properly. But now I think it's no more an issue. You see, I have hyperparameter opt. Again, some statistical concept. Think about, we talked about parameters that we define within our machine learning model, right? How do you know that those parameters is the one that is good enough for the model you're doing handle? If I turn on hyperparameter optimization, it's going to do what we call grid search. It will define bunch of range of all these parameters and carefully go through them and find the one that best optimizes your data. It's a very expensive process. You only run it once when you are ready to do a production calculation, meaning when you're ready to get the best parameter that you use to do your model calculation. So that's why I always set it false, because you don't want to be running it each time. Figures, but you need to save figures because this is already this. I'm telling you, the hardest part in machine learning is how to get your data. Data cleaning is how this will define all, right? Imagine when, and remember, there is no company that have or organization that have all their whole data clean and kept somewhere. You're going to have, you guys know what NAN is, not the number. You're going to get some column with NAN. You're going to get heterogeneous data set that don't conform to what you're looking for. You're going to get a bunch of other data sets that you need to actually see that by yourself and use Python tools to aggregate and arrange. You also need to do something like this is where domain expert comes in. You as the expert will now answer the whole. Remember, remember when you write y is equal to mx, that's the simplest linear expression. You write y is equal to mx of I plus c, right? In machine learning, your y is known as the target, while your x of I are known as the features. So imagine when you're to design a linear regression model with many parameters there, and your company or your organization or the university is cutting a lot of data. How do you select the ones that best define your linear model? That's what we call feature selection, or he or she will tell you that the hardest part in actual machine learning is not the training of the model, but the actual data collection and aggregation. In fact, 90% of your time is spent doing that, because the quality of your model is a function of the accuracy of the data that you're putting in, right? So that is what. You see, 0, 1, this is 0 Kelvin. These are the carbonite, the dicarbonite, 0 temperature, 300 Kelvin and 600 Kelvin. So how do we get this here? Another upload we need to do. So to go and find, this is how we get it. So this is how we get it. Click here. See where you need to click. Click here. And then find this place. Okay. Good. Now that it's clear here, you see. You can now upload. You see, you upload here. There are many things you can do here. You can also mount a drive.
Upload to session service.
Yes. Or you can do this. Come back here.
Yes, next to the desktop.
Go back. You need to go to remember it's inside data set. This go back to the folder you downloaded. You need the one the DH dash data. So you go to the file you just downloaded. You see 2DH dash data. Is this guy? Yeah. There are many ways you can do it. Let me try to drag and drop. You see?
So
I like dragging and dropping.
MX files, many of them inside.
But I already drag and drop.
The entire folder.
Yes, drag and drop. I don't upload waste my. That was the internet allow us. Let's see if the internet allows us. Remember, you see it's uploading. You see it's uploading, right?
Yeah.
But the internet is slow.
So you have to drop the whole information.
No. 2DH. Remember, see the file.
2DH.
2DH dash data, yes.
It's a folder. It's a
Yes.
folder, not a file.
I said it's a folder, not a file. I said the whole folder. The whole folder. 2DH dash data, yes. Why? We are not just dropping it sheepishly. We are dropping it because that is the folder holding the data that we want based on this extension. Look at this place. But the problem now is that we are stuck. The internet is not allowed. The folder, you drag it and see, drag it and dump.
I use upload.
Drag it, see. It's this. I don't want to do that. Because I already uploaded it.
can just copy it and
I didn't say copy, drag and drop. They are two different things. When you do that, you do something. Wait for it. It's going to go. Yeah, the network is. Last time network was 5 years. Okay, see what we're gonna do. Could you guys look up what another trick I want to do? I didn't intend to. The responses to the responses. Can you say it out? Because it's not just me and you talking.
For every machine learning task, is that all these are problems?
You have to write, right? But the algorithm is already there. Like right now, we have a grant here. We're actually designing this machine learning tool. We're using a mathematical output known as matrix factorization. So you can actually contribute to the actual machine learning, not just using the one that others are.
Minimize this.
No, sorry, this is the list, not. Could you I want to show you. The drag and drop is I click here. Now, drag and drop. Click on here and here. I'm trying to do one by one, it's still not there. No, it's responding, the internet is slow. If you do succeed, could you? So let's use this one. Mine didn't upload, so let's use the one that succeeded. What he did is, and I also tried that. Did you rename it? That makes it easy. So now we have to do some modification. Remember, so we have to do some modification. Now we don't have a folder anymore. So we have to modify this. We have to remove the 2D. Does that make sense?
Okay. Yes.
So we can do this automatically. Find and replace. Let me see if I'm able to do it. Or we do manually. I hate manual. You guys know what I'm trying to do? You can delete it manually. So I'm going to find control C control 5. You're going to see find and replace. Right? I click on it. I'm clicking it out. I don't know, I need to wait for some time before it comes up. Here we turn green once it opens up. It's still uploading. Could you come and click on this? I'm replacing with nothing. So I will say replace all. Say that, right? See, if you ask me, I've replaced all of them. Using your find and replace is a Microsoft listing file now. Is, you know. So remember, we have all the whole files we need now. Let's try to do something. The first thing you do is you need to call your library. You need to initialize your libraries. The problem, it's not even a problem. It's actually better I'm using a laptop because this is a free version. Mine is a big Google Colab. So this one is a free version. To tell you that it will still work in the paid version. It's just that you don't get access to GPUs and other features. But for this exercise, this will still be fine. To run Google Colab, there are many ways you can run it. Again, I hate manual level. You can do manual level. Manual level is, you see this cell? Okay. You see the cell as it is. You can come here. You see this arrow? You see the arrow? Click on it, it's going to run. It's running that everything that is in this cell. If there's error, it's going to put an error and tell us what the error is. Oh, it ran successful. What this means is that all these libraries that are called here comes default in Google Colab. You don't need to install them. But if you need to install a new one, it's very simple. Let's assume one of them, say pandas, did not allow you to install. Did not pandas. You know what you do? Let's open a new cell. You tap here. You roll your mouse here. It's a code, right? Click on code. It opens a new. To install a new library in Google Colab is as simple as doing this exclamation mark. You need to put it. You type P, install. Say, what do you want me to install? Inside all this library. Let's say you want to install, let's say TensorFlow. Right? Let's say TensorFlow. Even though we don't need it. Right? There are, if you don't want to click this step, you do Shift Enter. I'm going to do that one. Shift Enter will run that cell. You see, it's going to check and tell you that it is already satisfied. It turns out that TensorFlow also comes default. But if the library is not there, people install the name of the library, will install that library that you want. We already have NumPy. We imported NumPy as NP. Am I making sense? Everyone gives you a very streamlined way to install libraries. Pip install. Remember, you need to put the apostrophe mark at the back. Because what that apostrophe does is it makes that environment look like a bash terminal, bash environment. So now we have all our libraries. To load the data, look, you see the data we have pd.read_csv. Remember, CSV is a particular extension. Exactly, which is what the Microsoft Excel, old one, use it. The new one uses Excel now. So, but we can also import it. So you see, remember, remember we imported pandas as PD. So we are now using pandas to read all these files. So we are reading it as pandas pd.read_csv. This is the name of the file. Because it is indexed, as you notice, it's index separated, you now need to let her know that it is index separated. If we run this, God help us, there is no error. We read out the whole files. if there is error, it's going to tell you the error here. The error is what we call descriptive. It will give you a guide what the error is. Let me give you an example. Suppose for some reason I remove an S here. He said no such file or directory as this guy. If the error that you get is descriptive, it takes that, just come back here, Control Z, we undo it, then we re-import. Sorry. Those are your angles, your AADB. Remember, that's not the value here. This is a summary table that has the standard data point that guy provides. Do you have any questions? So if you take any pandas data and do data.describe, it will give you those things. It will give you the standard deviation, the mean, the mass, the total number of entries in the system, and other information that will guide you understanding. So remember I told you earlier on we imported what we call label encoder. Because generic Python environment or machine learning environment does not understand non-numerical data. If you look here, SG is a space group. It's not a number, it's symbolic, meaning it's, it's actually a number, but it's not the type of number that it will understand. Another thing here that we might not understand, the phase. Like remember we have 0 to 600. We use those level encoder to further clean the data. So another assumption, the space group is assumed to remain constant with temperature. That's what we are assuming. But it's not guaranteed. But whenever you're doing any modeling, you do some assumption. The probability of a material of a phase transition occurring within that regime of temperature is very, very small. So that there is no phase change. There's what we call a bond stability criteria. Anybody has heard about that? Bond stability criteria. Really? Come on. Now, for any material, for that material to be said to be stable, now C11 must be greater than C12. C12 can be negative, but C12 cannot be greater than C11. If those conditions are met, we assume that the material is stable. C12 can be negative because there's what we call aesthetic materials with negative Poisson ratio. Meaning, what that means is that instead of X, like we have a refrigerator, we use in cooling and things like that. Those materials are stored. Anyway, so now we do all this assumption. These are sound basic assumptions. Remember, which is what I was saying earlier on that you need a combination of a couple of things to do machine learning. One is domain knowledge. You must be an expert in an area that you are designing machine learning. An economist cannot design a machine learning format. He doesn't know what C11 is. He doesn't even know what the bond stability criteria is. Right? So it's a combination of the domain knowledge is more important than the machine because all these others are actually very easy to do. Honestly. So if we do that, we also run this column. This is not an error. It's telling you if this was run using maybe Python 3.7. We have Python 3.14 now. Many changes have occurred. But remember, these codes or Python environment are what we call backward compatible. Meaning old Pythons, well, sometimes they do break, but if they break, it will tell you the exact error. These ones are warning, they are not error. Am I making sense? Go to your import warning, and suppress it, and you will see the one. But let's leave it for now. So we do further data cleaning. Here, we separate C and space group Now this is where we are applying those conditions that we said before. We are now saying we only need this data for C11 greater than 0, right? Which is our bond stability criteria, and C11 greater than C12, and remember it is an AND operation. If you want the bond stability criteria, say that C11 must be greater than 0, and C12 must be greater than C11 must be greater than C12. So those are the rules we are applying here, right? And another thing, the space group will replace, there are some that are small, we kind of replace it with the more generic one, 52. And you can also display this. I think I'm still. You see an error now. It says SD in temperature dependent calculation assumed to be the same as this. So ND replaced X1 to third position, but 4 were given. So you see the error, right? So where do we have ND replaced? This is it here. You see? This is where the error is coming from. This is where the error is coming from. So, and it tells you what the problem is. It takes 1 to 3 positions, but 3 were given. But it's only 3 that but 4 were given. We don't have 4. If I want to delete this, how do you delete it? Go on. This is here. Could you comment out this one? Put hash. No, don't comment it out. Hash. No, you didn't put it well. Move it out. Put hash. Until we figure out how this computer works. Is it not? What type of computer? So we are renaming AA to A, BB to B, CC to C. It's just renaming. As I told you, there are many tools in Python that helps us get started. But I'm going to, I think it should be fine. So the ND replace again. Where do we have ND replace? Let's comment it out.
But maybe you need to see that here. This controls. But you must need it down.
Yeah, we'll just comment it out for now. It doesn't change the data we want to look at. As long as you keep it the same throughout. So this is another one. This one. Remember we had the OH, I mean the 0 Kelvin, the 300 Kelvin, and the 600 Kelvin. This is similar to what we saw last time, some warnings. Anywhere we see replace now. So what are we doing here? There are a bunch of replaces, but this replace is like iterative, meaning there's a loop. There's a loop here. Look at there's a loop. For I in math test, that is a loop. That is the way you do I see what is fortran. Right. So what is it doing? We are removing some of these materials that are not part of our initial structure, or I know what is going on there. These materials are small, meaning their group is small and they remove it from the data set. One, because telluride-based lead and the rest do not qualify for the type of, we need strictly dicacotinide and monocacotinide of the same family that qualify for that. So you can look through it. Remember, there are some comment out here. Here is also renaming. We are renaming columns A. We are renaming AA to the A, BB to the B, CC to the C. We already did that before for the 0 curve.
Is there a new way you can control the stability of those meters? Let and see, then
if you have MOS or PBSE is 100. You know from the chemical formula what the composition is, right? Not that we know how to control that, both experiment and computation. You know from the this place is getting dope, you're going to get your space group, you're going to get ABC, you're going to get your young model. That's all we care about.
But you can still simulate.
As I'm saying, it doesn't matter what you do because once you provide this, it becomes part of your database. Am I making sense? So we do bunch of, so remember we commented out this guy. So we comment out this replace again because it's for a bunch of data sets. So if you look at this one is the same as the one we already have. This is an again applying the stability criteria we already said. Similar for these guys too. Remember, the 0 Kelvin, 300 Kelvin, and 600 Kelvin. This is another one. So because we have a replace somewhere. So let's take this, let's comment out like this. Again, similar to this guy. There's a replace somewhere. So we aggregate as we did last time and conquer for the 300 Kelvin. That's what we are doing on this set. And you can now check the data set info. So data set.info, so if you take a pandas data set and .info to it, it's going to give you all the information. It's saying, remember, Python starts counting from 0. So put that at the back of your mind. It doesn't start counting from 1. He said you have 458 each of them have the same number of entries. So meaning there is no, you have there's no any and this. And it's telling you that phase is object and temperature is also object. Object means it is not a number. Remember, you have object, you have float. Float is numerical value in terms of value. So it's float. So here is saying float 64. Float 64 simply means double precision. For a float 32. Yeah, the other one is Python object, which is like a test. Even though it's a number, because space group is a number, it's actually an object because it's not numerical. Right? Again, we can check display again. But display, I prefer display because it looks more like, good to see you. This is nice format that is easier to look at. So here we want to reset index. So any space group number that is less than 4. Remember you have space group 1 to 2/3. So we want to remove further clean, remove the one that, why are we doing this? Because we want to at least make sure that the bulk of them has a hexagonal symmetry that E is equal to. So you can further isolate this guy here and iterate over it. I like the error. It states that up to 25% of what drives your machine learning algorithm is driven by C. It tells you that temperature actually does not play a huge role in the algorithm, right? So you have a way of streamlining which of them to include in your machine learning algorithm. And this feature tool for feature analysis helps you to do that. I'm going to go straight to here. So this is where you do your model selection. Here appear of sample statistics. What does that mean? After you train and test your model, you want to check how it behaves when you expose your model to the data that it has never seen, sample statistics or unseen database.
So we are taking 20% of our whole data set and isolating it completely, no interaction, so that we can use it to benchmark how accurate our model is after we do our test training process. And that's what this guy does. So we split it, you can see test size, we actually define it by hand, that is 42. Meaning anywhere I use a random state, you can see it here. Anywhere I use a random state, we have used 42. Meaning if you run this calculation, this job, you're going to get exactly what we got as at the time when we run it, independent of the version of Python that you're using. So it's always a good habit to define a random seed for a machine learning algorithm. So let's leave this guy. The what? Pseudo-random. So now we decide, remember what we're doing here is simply y equal to mx plus c. That's what we have here. We want to pick our feature. We want to designate one of them as y and the rest as a. That's what we have here. So here we have chosen the a as our y and the exactly. So that's what we have here. Now the first thing we do is linear regression. This linear regression, remember we kept 20% as an unseen data, on the actual 70-80%, right? So we take the remaining 80% and split again. We keep 70% for training and 30% for tests, right? Because the training and test go simultaneously. That's what we have. As you can see, our random seed is still 42 and test size is 0.3. 0.3 simply means 30%. So we split again. So we're going to get, so when we split, remember I told you about this K-fold, what we talked about, and the repeated K-fold and other stratification processes. You can see we are doing n split of 5. We are shuffling. Again, our random state is 42. So we take these remaining 70% and partition them into 5 because our n split is equal to 5. Am I making sense? Am I making sense? Score and cross validation predict. We imported it already. Then you see, we also get our root mean square, the scores, and print it out. Right? This is the first, this right here is the machine learning process. As simple as it is, this is the simplistic model. So we can run this guy. It's going to tell us the accuracy and code. Let's run our own first. So see what I mean. 0.79 accuracy with a standard deviation of 0.009. Remember, we share this into 5. Each of them will have 5. If you count, could you? How do I highlight this? No, the down one, the down one. If you count that place, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because it's going to be around 15 or so. Because it has 5 for the shuffle sheet, 5 for the cross validation. Each of them comes in 5 sides, but that's the way we define it.
That's what happened.
Exactly. Look at, see, we said we feed the training and test, the X and Y. You see, that is where you fit the actual data you have. Now, after you fit it, we do our repeated K4. You calculate the cross validation score. You check how accurate it is. Am I making sense? This right here, which is why I tell you that when it comes to machine learning, the data cleaning will take 90% of your time. The actual machine learning is very simple. In fact, there are tools in Google, meaning if you already have a clean data, you can plug it in there and it trains for you. Am I making sense? So that is that the hardest part of the process is the data cleaning process. That does not negate the role that experts play. Remember we talked about feature engineering, which is how do you select your feature, what guides into doing that, right? That also plays a role in this process. Now we can do some benchmarking. So this is, we plot the predicted and actual. This line here is guide to the eye. It's nothing, right? It's nothing. Well, guide to the eye meaning how far is the predicted from the actual. It's not that bad because most of them are sitting on this line and this one are, I'm using my hand, it's not showing. And this one's down here is further away from the line where the actual data is, which is still within 5%. DFT data, DFT Vanguard, that is the underestimation. Anybody have done calculation, you can do a DFT calculation and have a lattice constant of 8.52. I'll do my own and have a lattice constant of 8.5 or 8.49. That is within 10%. This right here is still within the numerical uncertainty. In fact, in this paper, we show that we can do better than DFT by getting it to around 12%. That is where the bagging and boosting models we talk about, like SG boost. This part is where, but I encourage you to run now, try to explain it. Remember I told you hyperparameter optimization. We define all these parameters, but we don't know which of them best describes our material. This is where we carefully calculate and look for the one that best accurately describes the hyperparameter optimization using what we call grid search. And that's what we do here. You see, we define a range of them and we define a bunch of algorithms. These are all bunch of algorithms. This right here could take a while for a very light system. But I'm going to just show you the one we've already done. So what this we do is going to do it for various machine learning models and do the hyperparameter and tell you which of the model best describes the system based on the arrow square and the mean square error. So you can see here, I've written down the best parameter here and kept it. So the best parameter for choosing model is this one, these numbers. And that is the number, and it tells that is the SG boot regression is the most accurate. Remember we had Bayesian, linear, SG boost, hard boost, a bunch of other models that we did hyperparameter on. So it tells us that the SG boost is the best. And based on that, we put all those optimized parameters here, right? And we rerun our machine learning algorithm using SG boost. I'm not going to run it because we didn't do the hyperparameter optimization and we don't have those numbers now. Not that it won't run, but it might give some error. So you can see, let me go to SG boost. The arrow square increased to 0.88 from 0.8 to 0.88. Look, did you notice something? Most of them are clustering within one place, meaning better prediction. So because this is a boosting model, it gives better accuracy to the other one. Now you have a model that you can use and do. Remember we kept 20% for out of sample statistics. We can now take those 20 and do some calculation. And that's what we do here. This is what we call prediction with the design element. We now take that 20% that we kept and check what is the arrow sphere for those guys. And that is the data here. If we do prediction with it, it's still 0.88. And you can see how clustered they are. Another thing we did here, but I don't think we have it here, is we actually went to literature prediction. So this notebook is, remember I commented out some things, right? It's fine, you can comment that part out. It doesn't affect our data because it's just renaming something. And the thing we are doing was the phase. We don't need the phase in actual calculation. So what I encourage you to do is try to run this calculation on your own. Meaning, when you finish setting it up, you know you can run all of them, run all at once. If you start from the beginning, since you're ending up, if you start from the beginning and run all of them to the end, now God gets an error. Yeah, remember this place. If I can let me copy this. See, this is the place we have an error which we do. You see where I'm commenting now because we commented out a couple of one line in each of the cells. So please comment out this part in your own. What I'm saying is there is a platform I'm designing, it's not ready. If I get that platform, we've got another error. Check on it. If I get that platform, yeah, there's nothing wrong. If I get that platform ready, it actually teaches you machine learning from scratch, so that you can learn it before you try to run this one, so that you can appreciate what you're running. Am I making sense? So I'll try to finish it. Those are software issues, but I'll try to do it for many things. But I should have it in 1 or 2 days. If I don't make it back here tomorrow, I will make those arrangements and hop in.